Good afternoon, everyone, and welcome again to another Can seminar. Today we have Dr. Lily Poulikakos giving a talk to us. So let me give her bio. Dr. Lily Poulikakos received her bachelor's in architectural engineering from the University of Colorado Boulder, USA, master's in civil engineering from the University of Illinois, and PhD in civil engineering from ETH Zurich in Switzerland. From 2001 to 2023, she worked at EMPA, the Swiss Federal Laboratories for Materials Science and Technology, where she held the position of senior scientist. Currently, she is active as an expert on national and European projects. Her expertise is on using multi-scale characterization methods to study innovative bituminous materials chemically and mechanically, with a focus on low-noise pavements and the use of waste and marginal materials for roads. She has been a leading member of RILEM as former deputy chair of the Technical Committee on Nanobituminous Materials and Chemomechanical Characterization of Bituminous Materials, and chair of the Technical Committee on Waste and Marginal Materials for Roads. Dr. Poulikakos is the author of over 130 publications on international peer-reviewed journals, and since 2018, she has been an editor of the Journal of Construction and Building Materials. So that's our pleasure to have Dr. Poulikakos here today. So let's give her a round of applause.
Thank you very much for the introduction. I guess I can share my screen now. Is that okay?
You can share your screen now. Yes.
And you can hear me well, I guess.
Yes, perfectly.
So can everyone see my screen?
Yes.
Okay, great. Then I'll start now. I'm going to talk to you about two topics today. One on alternative materials for roads and the other about quieter pavements. So noise and alternative materials. I'd like to start by acknowledging my colleagues. The projects that I'll be talking about today had three groups working on them. Two were from EMPA, the institution that I represent. So I'm coming from a concrete and asphalt lab at EMPA. We're also working with the acoustics noise control lab and also ETH Zurich. So there are materials aspects to the project, there are noise aspects to the projects, and there's a life cycle assessment aspects. And here you see on this slide the different organizations that are involved in mainly in the different aspects. So I'll start by giving an introduction, some facts and figures. I'll give you some sample of performance results on the binder scale and the mixture scale. And so anytime that we use alternative materials for roads, it's very important to also look at the effect on the environment. And that's on the one hand, and on the other hand, perhaps we can make these materials work mechanically, but does it really make sense to use these kind of materials? For that, we need a thorough life cycle assessment. And I'll give you some examples of that, and I'll finish with some conclusions. So first of all, on the topic of waste, there is a lot of waste that are gathered around the world, and these are some numbers from Europe. For example, you see concrete that comes from construction demolition waste. Every year in Europe, 350 million tons are generated, and about 260 are still available. So a lot of it is reused and recycled. However, still millions of tons of all these materials are still available. Perhaps some of them can be used for the road. And on the topic of noise, you see in the two paragraphs at the bottom of my slide, the World Health Organization has indicated that in the EU, the European Union, and Norway, traffic noise is the second biggest environmental problem after air pollution that affects the health of people. And also after particulate matter, noise is the second major cause of disability-adjusted life years. So it is very important to look at noise also and to look at waste. Both of those are substantial problems worldwide, although I'm showing you numbers that come from Europe, but these are not European problems. These are worldwide problems, and perhaps our industry can contribute to reducing these two particular problems. And if you visit any recycling plant like we did here in 2019, you'll see this is some of our team that was there. And you see that piles and piles of waste. In this case, it's plastic waste. I'll show you some results of the material that we obtained from this plant. So if you visit any of these plants, then the whole problem becomes a lot more urgent and that we should really do something about. Now, why do we care about using alternative materials? Well, it is because we would like to contribute to the circular economy. We would like to use basically raw materials that are environmentally friendly. Also, when we produce our asphalt mixtures in the construction maintenance phase, in the use phase, and end of life, throughout the whole life of the pavement, it's important to keep in mind that we need to consider the reduce, reuse, and recycle principles in order to contribute to the circular economy. Now, what are low noise pavements? Well, they are there is a definition for low noise pavements. They are pavement that should reduce the noise considerably in comparison to a conventional pavement, and that during the whole lifespan of the pavement. So here is a example that I can show you. If we compare the low noise pavement to a conventional pavement, in this case it's AC11. If we reduce the noise by 1 decibel throughout the lifetime, that is equivalent to reducing the traffic by 20%. If we reduce the noise by 3 decibels, that is equivalent to reducing it by 50%. And in this case, we probably would have to replace the pavement after about 12 years. This is what is done normally in Switzerland. And if we can reduce it by -6 decibels, then we can reduce the traffic by 75%. And if you remember what the World Health Organization has told us, that it is very important to reduce the noise and reduce exposure to noise. So if we can reduce the noise at source, at the pavement, then that's a very important tool that we have in our hands. And in Switzerland, what type of pavements, low noise pavements are used? Well, on the one hand, there's porous asphalt that has high air voids, and there's semi-dense asphalt with a little less voids, and then also in the texture can be also optimized. But as we reduce the noise, we also increase or reduce also the durability. So porous asphalt also has lower durability than the other options. So the different options also have different capabilities in terms of reducing the noise. Now we have published some papers about what the experience with alternative materials are within the available literature. And here I have some samples of the waste materials in the left column, and we've looked at rutting resistance, moisture resistance, stiffness, and fatigue. And we see that many of these alternative materials can perform better or similar to all virgin materials. And with the upward facing arrow, we're showing this. Now, so basically what we see in the literature, what our colleagues have shown, is that it's possible to use these type of materials. However, the technology readiness level for these different kinds of materials are not the same. So we've looked at this is the sample of the materials, and for example, we see the chrome rubber using the wet process has a very high TRL level. We estimated it to be from 7 to 9, and that means the application is partially or completely industrialized. However, there are other types of waste materials, such as recycled glass, with a low TRL that indicates the information there is only in the laboratory scale. So in our projects, we have looked at various types of materials, and I'll show you some results for that. Some of this is also geographically limited. So for example, the use of chrome rubber is widely used in some countries and it's forbidden in other countries. So there is a bit of knowledge gap when it comes to all of these materials. So we are using a multi-scale approach to look at the materials. We are looking mostly the information that we have is a centimeter scale, like for example, the indirect tensile strength or water sensitivity and so forth. But in addition, we have looked at the micro scale, the microstructure. We looked at chemistry. We have also looked at some select mixtures in the meter scale, and also we've looked at the life cycle assessment. And as you all must know, our material is very temperature sensitive, so we really need to look at the performance also at the various temperatures. And particularly since we are using alternative materials, that might make our mixtures more susceptible to cracking or to rotting. So it's very important to keep that in mind. The types of urban wastes that we have looked at here's some of them that I'm showing you. So 2 types of plastics and chrome rubber and electric arc furnace slag, recycled concrete aggregate filler, and PET are some of the materials that we have looked at, and I'll show you some of the results. So the materials, basically, we have used some of them as a binder additive and some of them as replacement for aggregates. After some initial screening tests, we have looked at the low temperature and high temperature performance of the materials, and selected mixtures have been looked at with a load simulator. We've done some leaching tests and some LCA on some of these selected mixtures. So I'll start by giving you some example of the binder results. What I'm showing you here is the binder that is exposed to the electrons in an electron microscope. And after a while, they develop these type of microstructures, these fibril formations. And the second sample that I'm showing here is the same binder with rubber in it. So the rubber introduces some disruption of these microstructures. Now, looking at the plastics, the recycling plant that I mentioned earlier, we were there and we picked up some of their materials. So they produce 16,000 tons of polyethylene per year. This is from packaging. And so they produce pellets from this waste, and they sell these pellets, as you see in the middle of the screen. However, in the production process for the pellets, they also produce a lot of waste, and that's what you see at the bottom. And this waste is used in the cement factory as fuel. So we picked up both of these plastic wastes and brought them into our lab, and added to our 7100 straight run bitumen, and looked at it under with our DSR. And what we saw is that both of the plastics, the red and the orange plot shows an increase in the modulus at the high temperature zone. So even more than our reference that was polymer modified, here it's shown in green. So we thought that there's a potential for this waste plastics to help in the high temperature range, for example, for rutting. However, so I will show you the mixture results in a few minutes. We also looked at viscosity. So here we're introducing a performance index, just a simple index that's a ratio of the performance of the waste containing material to the control that with no waste. And if, for example, the value is 1, that means that the performance was exactly the same. And we saw some interesting results. So we see the viscosity here with respect to temperature for the polyethylene is shown in blue and the chrome rubber shown in orange. And we see that there is an increase in comparison to the control in all cases. However, the trend seems to be different with respect to temperature. And that was very interesting for us to see that the results were different. Now, moving on to the mixture performance. Here in green, I'm showing you the surface texture. The surface texture is actually very important for the noise performance of the mixtures. And I'll show you some results from the various mixtures that we have tested. So again, as I mentioned before, it's very important to look at high and low temperature performance, as these materials might be particularly susceptible to rotting or cracking. And again, this is an electron microscope image of a chrome rubber modified mixture. And you see the different elements of our mixture that are present. You see the aggregates, you see the mastic with filler. However, there are also pieces of rubber that are still in our mixture. So why is that important? Well, when our mixture is cold, everything is behaving elastically. However, once the temperature goes up, our bitumen becomes viscoelastic. However, the rubber remains elastic. And this difference also adds to the performance. So I can show you some examples of that here. You see the results of the indirect tensile strength for 6 mixtures. 3 are asphalt concrete and 3 are SDA, the semi-dense asphalt. So you see, of course, the strength is lower for the semi-dense asphalt, both in dry state and wet state. And the AC1 and SDA1 do not have any rubber in them, and 2 and 3 in both cases do have some amounts of rubber. And you see that in almost all cases, there's an increase in the strength in dry and wet state. Only in one case, there was actually a decrease in the wet state, and that SDA3 had more rubber in it. And also the quotient of that would be the ITSR, the indirect tensile strength ratio, and all 5 of the 6 passed the requirement in Switzerland. So I'm moving now to another material. Most of construction demolition waste comes from Portland cement concrete that in German is called Beton. And you see here the amount that of the different contents for construction demolition waste. And also in the lower part of the slide, you see the different fractions. So we have added the construction demolition with different fractions of it to our mixture, or we replace the different fractions in our mixture. And so in black, you see the ITSR, the conventional ITSR, and we've also used other methods for indirect for water sensitivity. And you see that compared to the control, we also have several mixtures that do pass the requirements. So moving on now to cold temperature behavior, and now I'm moving on to the plastic modified mixtures. Now you see that using the semicircular bend test, our fracture toughness has decreased somewhat compared to our polymer modified mixture values. However, when we go up now to the high temperature range, we see that looking at the cyclic compression test here at 50 degrees, we have the number of cycles and the permanent strain. And we see that the two mixtures that include plastics could not meet the, the performance of the polymer modified mixture. So it did increase the performance from the straight run bitumen, but could not reach the PMB. So now looking, just putting all of this together, we have looked again, we can come up with the performance index with respect to the control mixture. And we see the different kinds of materials. Most of them could reach about 80% of the control. And depending on what kind of modification of the mixture we use, so it is possible to reach a good performance. Now I'm moving on to the larger scale characterization methods. Here we're using I'm showing you how we prepare the samples. These are large samples, large slabs that are produced using a frame and using a roller compactor. And you see that we are using a traffic simulator to test these. There are 4 wheels for this traffic simulator. It goes at a speed of 9 kilometers an hour and an axle load of 9.1 kilonewtons. And these tests were performed at 30 degrees. So basically we are testing for rutting, but on larger slabs. And so here I'm showing you an example of the chrome rubber modified mixture. You see in blue, that's the polymer modified mixture, and these are the two with the rubber. So there is more rutting for the two chrome rubber modified mixtures. However, the maximum came to below 6%, and also the absolute value of the rutting was below what is normally considered acceptable. So for example, for other tests, 7 or 10% are something that is acceptable. Also, we did these large-scale tests for the recycled concrete aggregate modified mixtures. This is only the filler was replaced. And so we see that we don't see any significant disadvantage of using the RCA filler for our mixtures in comparison to the control. So as I mentioned earlier, anytime that we use alternative materials, we do need to look at the environmental effects. So here I'm showing you an example of leaching tests. We've used the rolling bottle test for these. And so the Environmental Protection Agency from the US has identified 16 priority PAHs. Here you see these 16 PAHs and the pattern of leaches for reference SDA. And you see the pattern for only having chrome rubber. And in the middle, you have the mixture that has actually 1% chrome rubber. Excuse me, I'm losing my voice. So actually, so we see that the reference SDA and the 1% chrome rubber SDA have a very similar pattern. So we could conclude that the leaching was not due to the chrome rubber, but it is due to the asphalt itself. And I mentioned that we need to also look at acoustic performance. So the acoustic performance is affected by porosity, by mean profile depth that has to do with the surface texture and acoustic absorption. So here you see these three parameters for our reference and for all the mixtures that we have used. And several of these that I'm showing with the yellow arrow actually meet have very similar values to our reference. So they could have, it's possible to have similar noise reduction properties as with the waste materials. So I'm moving on now to the topic of life cycle assessment. I mentioned to you also earlier that we can make these mixtures work, but does it really make sense for them to use these mixtures? For that, we need to look at the life cycle assessment. And here we're showing the greenhouse gas emissions for chrome rubber modified mixtures. So we have a reference scenario that is actually without rubber and the test scenario that is a mixture with rubber. So in Switzerland, the chrome rubber is used as fuel for the cement factory. So if we remove this from the cement factory, then they have to replace it with primary fuels. And that is why the clinker production is higher. The greenhouse gas emissions for clinker production are higher for the test scenario. And that results in our test scenario being a little bit higher in terms of greenhouse gas emissions. However, if the waste management policy in the country is that the material is going to the landfill, then this image is going to be completely different. So we've gone through this exercise for various types of waste materials. And here is with a certain type of plastic. This is the chrome rubber. This is the recycled concrete aggregate filler and electric arc furnace slag. And we see that introducing again the performance index, we see that it is possible to reduce the greenhouse gas emissions by using alternative materials. So that brings me to the conclusion of my talk. I hope that I was able to convince you that many waste materials can be used as substitute for all virgin materials. We saw that we could reach about 80% of the performance for semi-dense pavements. It's possible that we have to do mixed adjustments and, for example, increasing the binder content or similar. And also we were able to see similar acoustic performance looking at some of the various type of parameters that affect the acoustic performance. However, we do need incentives, guidelines, and standards, and that's not always available in all countries. And so a thorough life cycle assessment and an environmental assessment is absolutely necessary when using any kind of alternative materials. And at this point, I'd like to thank you for your attention. I'd also like to thank Swiss National Science Foundation, the Federal Roads Authority in Switzerland, and also InnoSwiss for their support of the various projects that I showed today.
If we have questions here in the room. So yeah, Professor Haj.
Yeah, thanks. Really great presentation and very interesting studies. I have kind of two, I guess, main questions. One, in terms of the ESEM work that you showed, we've been working a lot with the environmental SEM, and I was wondering how you quantify what you see in that fibril structure as the beam damage happens, and how you see that relating to the performance of the binder later.
So we did not relate them to the performance. We just saw them as a characterization method. So we have seen that there is a change in the microstructure when we have, for example, chrome rubber in there. What I showed the fibril structures with the chrome rubber, there is a disruption of the microstructure, but I didn't. So we did not. So the microstructure changes, and there is a. We also have other results from, for example, rheology and so forth. So we did not see a direct change, but in some other works we have seen, for example, that aging changes the size of those of the fibrils. I don't know if you've seen some of our work. So with aging, we could characterize the change in those structures, but not necessarily for performance. So the performance would come from different testing, for example, using rheology.
Sure. Yeah, we did look. We saw. I think your group had some papers and also some others from Waterloo where they looked at aging, and we ended up looking all the way to 3 PAV cycles of aging actually, and saw very similar that the structure continues to change and has some relationship with where you see polymer degradation too. So we did explore that recently. The second question in terms of the waste materials, it seems like you guys are generally trying to maximize the use. So you guys are looking at using more of those. For example, I mean, looking at some of the rubber or plastic, a lot of studies are focused on adding to binder small amounts to try to improve or substitute for existing polymers. But it looks like your group is more interested in using larger amounts. Is the goal to maximize the use of waste? And if so, how is that looking in terms of the LCAs and things that you guys are doing? Even because as you showed, it maybe gives you 80% of the performance, not 100% sometimes, but how does that look in terms of LCA and environmental impact of that change in performance?
So, when we added, for example, plastic or chrome rubber, we can only add it a certain amount. And in this case, it was only 5% of the binder. So the larger amounts were when we replaced the aggregates. So we replaced the aggregates with different fractions of recycled concrete aggregates. We just tried to see what actually makes sense. And in terms of the life cycle assessment, what really affects the life cycle is reducing the binder a lot more than reducing the aggregates. So we didn't. The only place that we played around with the fractions was with the recycled concrete aggregates.
Good. Thank you.
Sure.
Thank you so much for the presentation. I also had a question on the life cycle assessment part. I was wondering, did you take into account the recycling of the materials? And if yes, how of impact did that have on the results?
If I understood it correctly, you're asking if the LCA included recycling. Is that correct? Well, in this case, no, it did not. It did basically, we did not use any wrap because we're using semi-dense asphalt and we're not allowed to use any recycled materials in there because it's a very sensitive material. It has to be high performance because of the noise reduction property. So they did not include wrap, but it only included waste material. So we only could compare the all virgin material with the material with wrap, with waste. So for example, with plastic or with different fractions of RCA and so forth.
Yeah, but what I meant is that, for example, for the plastic in the LCA, did you include the impacts of recycling the plastic, like processing the plastics to be ready to be used with the binder or the aggregate?
The impact of recycling? Yes, of course. I mean, basically what we did is that we looked at different scenarios. If this waste was not used in our material, or if it's used in materials. So we're comparing different scenarios. If, for example, the waste stream is used for using for other purposes, for example, polyethylene has a certain there's a certain waste stream. There's a certain use for that already. And if we take some of that and we put it into our asphalt, it's recycled materials, but in both cases, and we just compare the different scenarios. I'm not sure if I answered your question correctly, but
any questions in the room? Okay, Yusra.
Thank you for the interesting presentation. I want to build up on Lara's question. She asked about the processing of plastics, since you guys recycle these plastics and you reuse them as shredded parts. So in one of your slides, you were saying that there's a technology readiness level for using these alternatives. I didn't understand, how do you consider polyethylene waste and crumb rubbers or tires as like technology readiness level? If you may elaborate on that, like, is it in terms of processing, blending, or like, it's just not clear to me. And
okay, so the technology readiness level, that's what the TRL, that's the question, right? So basically that the paper that we have on TRL, it goes through the literature and looks at how plastics are used in asphalt. Like, how far are they? How far is it? Is it only used in the lab, or is it used on the road already? How far did technology go? So the technology readiness level is a scale. There are 9 levels, and the lower numbers means that basically this material is only used in the laboratory, and the higher numbers means that it is used. This technology is ready and used widely. It's not only test sections, but it's used regularly in the road. So that's we looked into the literature, the available literature, and we basically made that decision that, okay, there are test sections. This, for example, chrome rubber is used quite a bit. It's the use of it is much more advanced than other types of waste materials.
Professor Al-Qadi is also here, so he wants to.
Thank you for being with us today, Lily. I have a quick question. For the LCA, what databases were using in your analysis?
So we are using the databases that are available in Switzerland. I'm trying to remember now. They're the widely used databases. It's I don't remember the exact name right now, but it's just widely used databases.
Okay, so to follow up, like, you did measure the texture. Were you including these also in your LCA?
Excuse me?
Texture, you were measuring the texture for the mix.
Oh, the texture. No, the texture is not included in the LCA. No, it's only the mechanical performance is included in the LCA.
I see. Okay.
So the database is EcoInvent. EcoInvent is what was used. Yes.
Absolutely. Yes. Okay. Yep. Thank you.
Sure. We have a question also in the chat. It says, was the differences in performance of the alternatives considered in the LCA study? Yes, the difference in performance was considered. I mean, did you assume similar performance for the LCA? Did you incorporate the percentage of different alternatives in the LCA study? Yes, we did include the different performance for the different waste materials. But that is not so easy to do. I mean, we just used basically our laboratory studies, and we saw what the difference in the performance was in our laboratory studies. So we didn't have field studies for that. You can find a lot more detail in the papers that we have. I've referenced the papers in all the slides. So also if you can write me if you need some references.
Yes. Jose,
I think we also have someone,
you can unmute
Jose
yourself
Norambuena.
if he wants to ask a question.
So I can activate my camera. So really great to see you again. Thank you for your seminar. And hello everyone in the room. So usually, sometimes we have a confusion between the waste and secondary materials. That's my first question for you. Probably you clarify this concept. And the second one, my question is regarding your recommendations in order to use plastic waste, because it's a thermosensitive materials. But my question, you put the plastic inside the hot mix asphalt. My question is, what happened with the workability or something like that, using TGA or, you know, different tests in order to evaluate the plastic performance?
So yeah, we did use TGA. We did use TGA, but you know, when we the melting temperature of the polyethylene that we used is 120. So it is below our 160 degrees mixing temperature. So it really it was fine. It did not affect the polyethylene. And also you mentioned that the difference between waste and secondary materials. So basically waste, it's, I think that the whole concept of waste, we have to get rid of that because there is no waste. It's just other kinds of materials. And we have to get used to reusing these materials and thinking of how we can reuse them and if it makes sense to reuse them. So secondary materials are, for example, I showed you the polyethylene where, you know, you have a secondary material made, you know, after they make the pellets, there's a secondary material, a secondary waste material from production of the pellets.
Thank you.
Did I?
Just one more quick question. You mentioned about the different levels of noise reduction, and by far the porous mixture is the best option. But also this type of mixture is very sensitive to like variations in terms of materials and the application of waste or recycling. So what are your thoughts on these, like on the use of these types of waste as well for porous mixtures?
Well, that was a challenge, of course. It is, we are not allowed to use any kind of recycling in our porous mixtures. However, since this was a research project, we were able to do it. And we were, without doing a lot of trial and error, we were able to reach about 80% of the performance. So I think that if one looks deeper into that, then we see that it's possible to get the performance. And like we were able to get it. So it's not allowed right now, but there is no real reason for it.
We have another question here on the chat. What would be the difference in performance results if you modify the asphalt binder with powder-based plastic?
Well, we did not use powder-based plastics. We just cut them down to small particles, about 1 millimeter particles. So I can't answer your questions because we did not do an experiment with this. But the smaller the particles are, the more they will get more uniformly mixed into our mixture. Of course, that's an advantage. However, then there is also energy involved in producing these powders. So one has to see if it's worth, if you want to produce them at a large scale industrial level, then there is also cost associated to that. It's one thing to do something in the lab, and another thing if you want to go to a higher TRL and produce things industrially.
Okay, so I think we have no more questions here in the classroom. So again, thank you very much, Dr. Poulikakos, for being with us today. I know it's quite late in Europe now, so we really appreciate you being with us today. And again, let's give her.
Well, thank you very much for having me, and thanks a lot for your questions. Please don't hesitate to write me if you have any more questions.
Thank you so much.
Okay.
Appreciate you.
Bye-bye.
Bye.